Okay. So, lecture 6-9, proportional lead lag controller design. Proportional lead lag controller design is much like PID controller design, but the resulting controller does not require active compensation. The usual thing with these lead and lag compensators not requiring active compensation or active elements to instantiate. With our technique of cascade compensation for lead and lag compensators, one can simply apply both lead and lag compensation in the usual manner. The order of application can be somewhat important because lead compensation can impact steady-state error. So a way to proceed is as follows. Design a P controller and evaluate its transient response performance. Apply lead compensation to improve the transient response. Simulate to verify the transient response performance. And then apply lag compensation to improve the steady-state error performance. Check all performance criteria and adjust gains in 0 locations as needed. So that's our process. Nothing too surprising is going to happen here, but we'll just do an example. So let a system have the plant transfer function given in 660. Design a proportional lead lag controller such that the closed loop overshoot is less than 20%, settling time is less than 0.7 seconds, and the steady state error is less than 3%. What's interesting about this transfer function? What pops out? Yeah, it's negative, right? Do you guys remember that this is sufficient reason to tell us that this is an unstable system? If you have a negative coefficient in your polynomial, then the transfer function is unstable. So that means we have an unstable system that we're going to control. I've told you before that this is possible, and then I realized I hadn't done an example of it. So here we are. We have an unstable plant, and we're going to try to control it. First off, we have to determine psi, which is essentially to translate these performance criteria into location for our dominant closed loop poles to meet our transient response performance requirements. We use MATLAB. First, we must determine what the specified transient response criteria imply for locations for closed loop poles. Let one of these desired pole locations be called psi. The transient response performance criteria are as follows. Settling time 0.7 seconds, percent overshoot 20%. The steady state error 0.03, which is a fraction of 1. The second order approximation from chapter 3 tells us that the overshoot requirement implies a specific damping ratio zeta, or equivalently angle of our design point psi. Pi minus the arc cosine of zeta. Additionally, the settling time requirement implies a specific real part of psi via the relationship that the settling time is equal to -4 over the real part of psi. You're probably remembering this equation with zeta and omega n in it, and it being positive, but they're equivalent. So I just do that programmatically. I compute zeta from the overshoot. I compute the psi angle from this equation, 661. I compute the real part of psi from the settling time. And I compute the imaginary part using trigonometry from this psi angle. Okay? And then I print it out, and this is the location of our design point, negative 5.7 plus J11. Okay, if we do P control, then we'll try to get as close as possible to psi, and we'll do a root locus first. Comes out looking like this. Clearly, our design point's like right here. Clearly, we're not going to get there on the root locus. We're going to want to use either derivative compensation or lead compensation. All right, either one will work for us. So we're going to use lead and lag here. But if we do choose a gain of 5, we at least match the required percent overshoot approximately, which is somewhere around there. This was like K1 equals 5. So we're definitely not there, but at least we'll start with a P control that's as close as we can get. Okay. Now we do lead compensation. So we use cascade lead compensation with compensator given in 664, where we've got a gain associated with it that will start off as 1, and then a 0 location and a pole location. So let's set arbitrarily the lead. This should be, the D should be in the subscript. P lead should be at negative 30. That's pretty much arbitrary. We kind of want it to be out to the left because we expect that it'll affect the response, or it'll affect the second order approximation less if it's out there. So from equation 638b, we compute the compensator 0. So we first figure out what the angle contribution should be, and then we find out from trigonometry essentially where the 0 location should be. And this was the same way we did our lead compensation before. We found out that the lead compensator should contribute 48 degrees of phase to move the root locus through our design point psi. And the pole contributes 24.7 degrees of phase. And so we need the 0 to contribute the rest of that. And so that implies the 0 location has to be at negative 9.19. By construction, this is on the root locus now. By construction, the psi value is on the root locus. So we can find K2 directly from equation 6.2, which just tells us how to compute the required gain. And we printed out 6.45. Now let's compute the closed loop controller C lead and the closed loop transfer function G lead using this. The C lead was already computed, so then we just used it to compute the closed loop transfer function G lead. Great. Lag compensation. So we have what was the system type here of our plant? Type 0. Even when we put in the lead controller, we added a pole, but not at the origin. So there's still type 0. So we have a type 0 system. A type 0 system needs to have an integral to go to 0 for its steady state error. If you're going to do lag control, though, we can reduce the steady state error by putting a pole close to the origin, which we now do. And then we'll put a nearby 0 to offset the effect. So this is the lag compensator. We'll start off with the gain being 1. Steady state error for the lead compensated system is given by the following. So we evaluate what Kp is. Remember the position constant for steady state error, and that's KPLD. And I estimate, and then we say, okay, we compute now what the steady state error would be for the lead case. And notice that I'm doing this not for the plant transfer function, but for the plant and the compensator, the lead compensator in there. And that's important because the lead compensator included these pole and 0 locations that affect the finite steady state error that we have for a step input. So I include them in here, and then I say the steady state error, it comes out to be 0.113. This is for a unit step input. So it's at like 11%. It's negative, which we haven't really seen before probably because we have this negative sign that shows up in our transfer function. And all that means when your steady state error comes out negative is that the output is larger than the input. So the error is not below the steady state value, but above the steady state value. Totally fine. So what we want to do, it's kind of convenient for us to choose our compensator location based on the this idea that if we know a factor by which we would like to improve steady state error, we can use that to determine the ratio of pole location to 0 location. And in order to compute that, we need to figure out how much improvement we need. We divide the steady state error requirement into the lead compensator steady state error. I take the absolute value because at this point, this negative sign is not useful in terms of determining the ratio. So I need the steady state error to improve by a factor of 3.75. And I choose somewhat arbitrarily my lag pole location to be at negative 0.1. Remember, the idea is to be close to the imaginary axis, but if you get too close, the steady state compensation takes a long time, right? So we put it close, but we don't put it too close. So negative 0.1, we could adjust that later if we choose. Then we want it to improve by a factor of alpha, 3.75. So we put the 0 then at alpha times the pole location, so alpha times further to the left, which in terms of the transient response is really pretty close, right? It's like instead of being at negative 0.1, it's at negative 0.375. So the pole and the 0 for the lag compensator are pretty close to each other. Great. Then we construct the compensator transfer function. We do the nice feedback transfer function calculation. And then it's just down to simulating. Okay? Now we just simulate what happens for the closed loop transfer function with P control, with P lead control, and then with P lead lag control. We look at the figure 6.21. We see that with P control, first of all, our overshoot and settling time certainly seem too big, and our steady state error is too big, right? So the P lead fixes the transient aspect for the most part, but it has an issue fixing the steady state error because it ends at like 1.1 instead of 1. So that's that 0.1 error, right? 10%, 11% error. And so we see with our lead lag, the yellow one, that we actually are reducing that steady state error down. But it's slow, right? It's slow. And also notice that we kind of screwed up our transient a little bit when we added that lag. That transient got a little worse. And so let's look at using step info. With peak control, the settling time, it was supposed to be 0.7. Clearly, we're not there. Percent overshoot 16, that's actually good. We were able to meet the percent overshoot requirement. The lead control, settling time 0.69, so that's good, close to 0.7. And the percent overshoot 17, so that's good, but the steady state response is not met, right? Because it stays, steady state is still 11%. We need it to be less than 3%. So then using step info, this P lead lag is not very helpful with step info because it hasn't settled completely, right? At the end of the simulation time that we did. We probably should simulate it out longer and see where it ends up. But also the step info doesn't take into account the fact that it came to a settling point here in about the same amount of time as the other one, and the percent overshoot is really closer to this relative sort of steady state value. So it's not great, but we can see that the transient response is pretty similar for the lead lag, and then we also get this steady state compensation here. So it's pretty good. What we run into though is a little bit of a quandary because we can speed up this lag compensation. We can speed up this steady state error reduction by a couple different means: moving the poles and zeros in our compensators, increasing the gain, etc. There are ways to do it. But when I was playing with it, I didn't do a very extensive search, but when I was playing with it, I noticed that we were really trading off going over our percent overshoot. As you adjust it, the percent overshoot kept increasing from here. So really, speeding up our steady state compensation is hard to do in this problem. So we're pretty limited there. So we're probably stuck with a slow steady state compensation, or we have to break our percent overshoot spec requirement. So we have this balance there, and you can explore it and trade off if you like. We should check our steady state error, because this is not a good reflection of a steady state error being less than 3%, because it hasn't gotten anywhere near steady state yet. So we could simulate it for a lot longer, or we can actually evaluate it analytically, right? We can check the steady state error based on the full transfer function with the compensator in it. And we do that. We compute KP, compute the steady state error, and we get that it is negative 0.0277, which is less than 3% per the requirement. It's 3% on the high side, right? So that may or may not be important to you, but 3%, within 3%. However, the compensation does take a relatively long time to approach this small error, so it's important to keep in mind. Yeah. So any questions on this? One important thing that we had to, so like pretty much this is just doing lead and then doing lag, right? Like nothing too exciting that's new here. But one thing we did have to do is recognize that the lead controller definitely affected our steady state error. It happened to improve it, right? I mean, it was an accident. We weren't trying to improve the steady state error between the proportional control to the proportional lead, but we did improve it. It went from being like 24% to being like 11%, which is better. But if we had done this the opposite way, and we had done our lag compensator first, and we did our lead compensator, we could have made it worse when we put that lead compensator on. So it's good to recognize that the lead compensator does affect the steady state error, so it's best to do that one first. And then the lag doesn't affect transient too much. So there's that. Okay. Do you guys feel like you're getting the hang of these root locus design problems? Yeah? Because this is the last lecture on them. So. Any questions on this one before I move on? Okay.